Beneath the massive swirling clouds of Jupiter lies a world that has never truly been explored. What happens below those clouds is far deeper and far more complex than we ever imagined. The storms on Jupiter don't just float on the surface of its atmosphere. They may plunge hundreds of kilometers deep into the planet's interior. Beneath layers of hydrogen and helium, Juno has detected an asymmetric gravitational field, suggesting that Jupiter's core might be a fuzzy core, where rock and metal gradually dissolve into the surrounding gas, blurring the very boundary between solid and gas. What is really happening inside? Have we reached the true heart of Jupiter? Or are we only gazing at the first layer of a far greater mystery? From its colossal storms to its undefined core, each discovery made by Juno is forcing scientists to rewrite everything we thought we knew about this giant planet, and perhaps even rethink how every gas giant across the universe is born. Prepare yourself. We're about to venture closer to these mysteries than ever before. When we look up at the massive swirling storms and bands of gas encircling Jupiter, what we're really seeing is just the surface of something far more powerful and mysterious. A hidden system of unimaginable depth. If the deep convective flows beneath those clouds are the planet's breath, then at its very core, where no light can reach and pressure crushes all known forms of matter, there lies a colossal engine of energy, Jupiter's moving metal heart. At depths where pressure exceeds 3 to 4 million times that of Earth's atmosphere, and temperatures soar to tens of thousands of degrees Celsius, hydrogen, the most abundant element in the universe, is squeezed so tightly that its electrons break free from their nuclei, forming a strange new state of matter known as metallic liquid hydrogen. Under these extreme conditions, hydrogen ceases to behave like a gas or even a normal liquid, and instead becomes an almost perfect electrical conductor, functioning like a vast ocean of metal. It is this material encasing Jupiter's core that creates a deep conductive ocean, where intense flows and the planet's rapid rotation, it completes one spin in just about 10 hours. Combine to generate a powerful dynamo effect, the source of the strongest magnetic field in the solar system. But perhaps even more astonishing is that this heart is not still. According to data from Juno and analytical models, an unusual magnetic anomaly near Jupiter's equator, known as the Great Blue Spot, is steadily drifting westward at a rate of about 2 degrees per year. Scientists from Harvard suggest that waves and oscillations deep within the metallic layer may be driving this movement. This, first and foremost, is evidence that Jupiter's core is not a fixed solid mass. It's alive with dynamic activity. Metallic flows twist and swirl, like veins of energy and magnetism. Magnetohydrodynamic simulations reveal that as the metal heats, it rises. As it cools, it sinks, creating a continuous cycle of regeneration, much like the heartbeat of a planet. When scientists observed variations in Jupiter's magnetic field through Juno's data, it offered a glimpse into the inner workings of this hidden machine, revealing that what lies beneath is constantly evolving. But why do these inner flows connect so strongly with the magnetic field and even influence the moons themselves? The enormous magnetic field generated by this conducting layer doesn't just envelop the planet. It manifests as powerful auroral pulses, hundreds or even thousands of times stronger than Earth's northern lights. As the metallic hydrogen churns, it drives electric currents that produce magnetic forces, which then interact with Jupiter's atmosphere, plasma environment, and surrounding moons. For instance, Io, one of Jupiter's moons, is directly affected by electrical currents flowing between itself and the planet, triggering extreme volcanic activity that shoots material hundreds of kilometers into space, a phenomenon confirmed by Juno and other observations. Research in 2024 showed that Jupiter's magnetic and plasma environment could provide substantial energy sources for its icy, rocky moons. Moreover, gravity and magnetic measurements from Juno reveal that Jupiter's internal structure differs drastically from the simple gas planet once imagined. Its core is not a small, compact rock, but rather a diffused core, where solid materials, metals, and liquid hydrogen mix, extending to roughly 20% of the planet's total mass, depending on the model. This is a crucial discovery. The heart of Jupiter is not static. It's fluid, dynamic, and ever-changing. Paradoxically, despite this intense internal activity, almost none of it is visible on the surface, and that invisibility makes it even more mysterious. The violent winds, storms, and ammonia clouds that rage above are merely surface expressions of something deeper. Why does this hidden machinery dictate the fate of everything above it, from the core to the clouds, even to the moons? Here, we begin to see the connection between two seemingly separate worlds. The deep gaseous layers, the planet's breath, and the metallic heart, the generator and regulator of its energy. Recent data also reveals that Jupiter's changing magnetic activity over time isn't a small detail. It's compelling evidence that the inner engine is transforming, perhaps in cycles or through interactions with its outer physical layers. Could this very metallic heart be the reason for the Great Red Spot's persistent survival? Perhaps it is the deep internal dynamo that has fueled and sustained this immense storm for centuries, not merely a simple atmospheric phenomenon. From seismic readings to gravity and magnetic field data, scientists have discovered that Jupiter's intense jet streams extend about 3,000 kilometers deep. And its magnetic field is not a simple dipole, but a tangled web of complexity. This means the core's activity is not isolated from the atmosphere, and therefore, the planet's heart can directly influence its skin. Next, we will descend deeper into the mystery of the Great Red Spot, the massive pressure valve that may be the most visible expression of this moving metallic heart. If Jupiter's metallic heart is the living soul pulsing within the planet, then just above it, amid its vast swirling cloud layers, exists a phenomenon humanity has watched for over 3 centuries. The Great Red Spot. There, within a massive ocean of gas, a colossal crimson storm spins with terrifying force, persisting for hundreds of years as if Jupiter bears an open, living wound that never heals. But is this truly just a storm? Or could it be an energy portal, where the hidden power of Jupiter's metallic core breaks through to the surface? Since the 17th century, humans have observed the Great Red Spot through telescopes, yet it wasn't until Juno entered Jupiter's orbit in 2016 that we began to understand that this phenomenon runs deeper than anyone imagined. Data from Juno's microwave radiometer, or MWR, and gravity science instrument revealed that the enormous vortex isn't just a surface storm. It extends roughly 300 to 500 kilometers below the cloud tops, into regions where the pressure far exceeds anything that could exist in Earth's atmosphere. At such depths, pressure can reach 40 times that of the ocean floor on Earth, and temperatures are high enough to turn ammonia and water molecules into ionized plasma. While storms on Earth last for weeks at most, Jupiter's Great Red Spot has raged since at least 1830, and likely much longer. However, recent spectral analyses and imaging show that it's changing, shrinking in size, becoming more distorted, and showing unstable outer edges. In 2024, scientists at the University of the Basque Country released findings suggesting that the current structure may not be the same storm first observed in the 17th century, but rather a reborn version, the result of deep energy flows continuously regenerating it from below. In other words, the Great Red Spot is not eternal. It survives through a self-renewing energy mechanism. The planet's long, slow breath Recent data from the James Webb Space Telescope has opened an even newer perspective. In the mid-infrared spectrum, the region surrounding the Great Red Spot emits strange oscillations within its ionized layer, where plasma directly interacts with Jupiter's magnetic field. Scientists have detected gravitational and plasma waves moving upward from the planet's depths, creating bursts of light in the upper auroral zones. This indicates a direct link between the planet's deep internal dynamics and its surface atmosphere. As if the Great Red Spot is a window through which energy from Jupiter's core escapes into space. What allows this storm to endure for so long? NASA's numerical models suggest that inside the Great Red Spot lies a double vortex structure composed of opposing convective rings, forming a natural energy lock that sustains itself in Jupiter's extreme environment. When upper-level winds lose energy, the lower layers replenish it. When pressure builds up, heat from the core rises to restore balance. It is a dynamic equilibrium, a living balance between centrifugal force, the Coriolis effect, and the deep convective heat of the planet. In other words, each swirl of the storm may help regulate or absorb electromagnetic energy from the core, a self-regulating magnetic feedback system that scientists are only beginning to comprehend. A new hypothesis proposes that the Great Red Spot may function as Jupiter's natural energy exhaust valve. Like a colossal volcanic vent, it releases excess energy from the metallic core, preventing the planet from falling into thermodynamic imbalance. As the core gradually heats up due to compression and convection within its metallic hydrogen. The energy moves upward through rising gas currents and is finally expelled through the most stable outlet, the Great Red Spot itself. The storm, therefore, isn't just an atmospheric byproduct. It's part of the planet's physiology, a place where Jupiter breathes. Spectral observations have also uncovered periodic oscillations within the storm's reddish hue, possibly linked to the chemical changes of photochemical compounds in the atmosphere. When deep energy is released upward, molecules like ammonium hydrosulfide and phosphorus pentoxide become ionized, producing the signature red color we see. That shade of red isn't constant. It subtly shifts in cycles over the years, proving that the storm's chemistry, too, is influenced by deep internal energy variations. Observations from Hubble and Juno in 2024 revealed that the storm is slowly drifting southwestward, about 2 degrees per year, matching the movement of the Great Blue Spot. A magnetic anomaly near Jupiter's magnetic equator? Two seemingly separate phenomena may in fact be linked. As the planet's metallic heart moves, it creates magnetic fluctuations that ripple outward through its layers, driving the migration of the Great Red Spot. If this storm truly acts as the planet's energy regulator, its disappearance could trigger profound changes in Jupiter's convective balance, thermal equilibrium, and even its global magnetic field. A giant planet without an exhaust valve could enter a phase of instability. where trapped internal energy builds to the point of completely restructuring its atmosphere. Atmospheric simulations published in 2025 have already suggested this outcome. In models without the Great Red Spot, convective energy becomes trapped deep below, spawning numerous smaller yet far more violent vortices, like a body deprived of its breath. That's why understanding the mechanism of the Great Red Spot isn't merely studying a storm, it's understanding how Jupiter sustains its own life force. And perhaps what makes the Great Red Spot truly magnificent isn't its size or its color, but its planetary function. Every swirl, every gust, every plasma surge within it is a heartbeat in the circulatory system of the gas giant. When we look at it through Juno's lens, we aren't just witnessing a storm. We are watching a planet breathe. If the Great Red Spot is Jupiter's massive valve releasing energy from within, then its entire atmosphere, spanning hundreds of thousands of kilometers, filled with turbulent bands of clouds and violent jet streams. This is a colossal machine in motion. This is not merely a chaotic gaseous layer, it is a stratified physical system, a measurable framework of dynamic architecture, intimately connected to the planet's inner mechanics. From the outermost cloud tops down through the deeper layers and all the way to the metallic core, each tier functions like a gear within this planetary engine. The latest observations from NASA's Juno mission reveal that Jupiter's atmosphere is divided into at least 3 main cloud layers, each distinct and well-structured. The uppermost layer consists of bright white ammonia clouds, where cold vapor freezes and reflects sunlight. Beneath it lies a yellowish layer of ammonium hydrosulfide, evidence of a complex chemical blend of sulfur, hydrosulfide, and ammonia. And deeper still, Juno's microwave data uncovered a vast superheated water layer that may contain hundreds of times more water than all of Earth's oceans combined. The presence of such a water layer under extreme pressure and temperature confirms that Jupiter's atmosphere is not simply a floating mass of gas. It is an intensely active chemical and physical system where elements and compounds continuously circulate both vertically and horizontally. Even more remarkable, scientists have detected ammonia rain, or more precisely, frozen pellets composed of ammonia and water within Jupiter's middle atmosphere. These are known as mush balls, icy ammonia clumps that form high above, absorb excess ammonia gas, and fall downward where they melt, creating a vertical exchange cycle of matter. This process not only depletes ammonia in the upper layers, but also alters the planet's overall chemical and thermodynamic balance, turning Jupiter into a living system, constantly rebalanced by flows of matter and heat. One of the most astonishing discoveries is the true depth of Jupiter's zonal winds. Scientists once believed these strong jet streams were confined near the visible cloud tops. Yet gravity data and updated models show that these winds plunge roughly 3,000 kilometers, or possibly deeper, into the gaseous interior. At those depths, pressure and temperature rise hundreds of times above surface levels. Yet the winds still blow fiercely, sustaining the planet's iconic light and dark bands. This deep connection between the surface atmosphere and the planet's interior proves that the atmospheric engine isn't operating in isolation. It's driven directly from within. The mechanism may work like this. Heat from the core and inner layers pushes material upward, triggering strong convection. As rising gases encounter dense hydrogen-helium layers, they are redirected into horizontal jet streams, carrying energy outward toward the cloud decks, and eventually releasing or redistributing it into space. Thus, each current of wind and each band of clouds forms part of a vast circulation system of vapor, heat, and motion, the planetary equivalent of breath. At Jupiter's poles, Juno has uncovered one of the most extraordinary atmospheric formations, stable storm clusters. Massive cyclones arranged in near-perfect geometric patterns, rotating around a single central vortex at each pole. What's remarkable is that over many years of observation, these storms have barely shifted in position or shape, even as the planet's upper dynamics constantly fluctuate. This stability defies conventional meteorological models, which predict that such giant vortices should dissipate rapidly on a fast-spinning world like Jupiter. Combined with the discovery of deep jet streams, these polar structures suggest that Jupiter possesses an exceptionally strong aerodynamic framework, where massive cyclones act as stabilizing systems, distributing energy and maintaining the balance of the entire atmosphere. This raises a profound question. Could the poles themselves serve as the planet's regulators, keeping the atmospheric machine in check and ensuring its stability over millions of years? There's another fascinating detail. Jupiter emits more energy than it receives from the Sun, a mystery that points to a powerful internal energy source. Studies indicate that this deep atmospheric engine, with its stratified clouds, vertical winds, and mushball-driven material exchange, plays a central role. Heat from the core travels through the atmosphere, redistributing into the cloud layers, the polar regions, and eventually radiating outward into space as auroras, plasma bursts, and electromagnetic emissions. Jupiter, in this sense, functions as a natural laboratory where convection, fluid dynamics, magnetism, and plasma physics converge in one colossal system. And if this is true, then every component of this atmospheric machine is more than a random phenomenon. It is a vital part of the planet's living cycle, matter rising from below, clouds forming, deep winds circulating, and energy released into space. By understanding this mechanism, we not only uncover Jupiter's secrets, but also gain insight into how giant exoplanets, the so-called super Jupiters, might operate far beyond our solar system, worlds we can only watch from a distance. We have passed through Jupiter's turbulent cloud layers, witnessed its colossal storms spinning for centuries, and traced the powerful jet streams that plunge nearly 3,000 kilometers below its surface. Yet, there is a place deeper than any storm or current could ever reach, a sacred, unseen realm, the core of the giant. Within it lies the answer to the greatest question of all: what truly drives the heart of this massive world? For decades, scientists believed Jupiter, like other planets, possessed a solid core, a distinct heart forged from rock and heavy metals. But ever since NASA's Juno spacecraft entered Jupiter's orbit in 2016, that long-held certainty began to waver. Precision gravity measurements collected over years, accurate to mere millionths of Earth's gravitational acceleration, revealed something extraordinary. Jupiter's internal mass was not distributed as expected. In 2021, the Juno science team published a groundbreaking paper in Nature Astronomy. Jupiter does not have a solid core. Instead, its center is a diffused core, a vast, indistinct region where rock, ice, and metallic hydrogen blend together in a supercritical state. There is no clear boundary separating the core from its surrounding layers. Only a vast, swirling ocean of matter that constantly melts, mixes, and flows. As one descends inward, the pressure within Jupiter rises to nearly 70 million times that of Earth's atmosphere, while temperatures exceed 20,000 degrees Celsius, enough to break apart ordinary atomic structures. In such conditions, hydrogen, the universe's lightest element, ceases to exist as a gas. It becomes a metallic liquid, conducting electricity even better than copper. Under this crushing pressure, atomic nuclei and electrons no longer remain separate. They merge into a metallic plasma ocean, dense, fluid, and electrically alive. And within that realm, Jupiter's core is far from static. Gravity data reveals that this diffuse region extends across nearly 50% of the planet's radius, spanning more than 35,000 kilometers. Rather than a compact central sphere, the core appears to be a slow, swirling storm of heavy material stirred by enormous convection currents, blending seamlessly into the metallic hydrogen envelope around it. This means Jupiter is not stable in the way we once imagined. Inside it, a constant process unfolds, a heart that shifts and reshapes itself endlessly. But what caused Jupiter's core to become so chaotic? Why didn't it condense into a solid form like Earth or Neptune? A compelling hypothesis emerged once the diffuse core model was confirmed. In the early days of the solar system, Jupiter likely suffered a colossal collision. In 2022, simulations from Osaka University suggested that around 4.5 billion years ago, a protoplanet roughly 10 times the size of Earth slammed into the young Jupiter at a velocity of tens of kilometers per second. That impact was powerful enough to shatter Jupiter's primordial core, stirring its entire interior into a molten mixture. The released energy caused the solid core to dissolve into the planet's gaseous layers, forming the diffused region Juno now observes. This ancient collision shaped Jupiter's magnetic field. Rotational momentum, and even the long-term stability of its atmosphere. If this hypothesis is correct, then the diffuse core we see today is the fossilized scar of the solar system's chaotic birth. Juno's plasma wave sensors have detected ultra-low frequency vibrations emanating from deep within the planet. When converted into sound, they resemble the slow, resonant breathing of a colossal living being. Deep, rhythmic, and almost organic, these oscillations are not random echoes. They are evidence of an active dynamic process, a system where heat and mass circulate slowly within. Such internal motion could be the indirect source of Jupiter's immense magnetic field, which is 20,000 times stronger than Earth's, and may explain why its magnetic poles constantly drift. NASA's latest models from 2023 suggest that convection currents rising from the diffused core play a vital role in sustaining Jupiter's polar storms and the dazzling auroras that stretch thousands of kilometers above its upper atmosphere. From the core to the outermost cloud layers, Jupiter appears to transfer energy in a way unlike any other planet ever observed. What happens beneath Jupiter's surface may well be the power plant that drives the entire planet. A closed feedback loop connecting the core, atmosphere, and magnetic field, where every component interacts with the others, a vast, living, dynamical system without beginning or end. Understanding Jupiter's core is not merely about knowing one planet. It could reshape our understanding of countless others. Over 70% of all exoplanets discovered in the past decade are extrasolar Jupiters, enormous gas giants orbiting distant stars. Discovering that Jupiter's core is not solid opens the possibility that many of these worlds too may possess diffused, melting hearts, alive with motion deep beneath their clouds. From the discoveries that pierced its dense clouds, Jupiter is no longer seen as a silent gas giant. It is a living ecosystem of energy, complex, dynamic, and deeply alive. The data paints a portrait of a planet with an interior stretching hundreds of kilometers deep, where the motion of its melting diffused core and metallic ocean perpetually powers its colossal atmospheric engine. This continuous transformation turns pressure, heat, and magnetism into the rhythmic pulse of an entire planetary system. Jupiter, with its immense magnetic field and inner vitality, suggests that life could exist in places far from the sun's light, sustained not by starlight, but by the planet's own internal energy. As the energetic center of the solar system and the silent guardian of Earth, every bit of data Jupiter reveals answers more than questions of structure. It speaks to the origins of planets and the boundaries of life in the cosmos. Beneath those endless clouds, Jupiter emerges as a vast, living chronicle, a cosmic diary that may hold the clues to our past and perhaps to the future of life beyond Earth. Thank you for staying with WUFO Space until the very end of this journey through the vast universe. If you found this video interesting and insightful, don't forget to like, share, and subscribe to WUFO Space so you won't miss our next cosmic adventures. Your support means the world to us and fuels our passion to keep exploring the wonders beyond.